All right, we've closed the doors so we can begin. So not an intimate crowd, so that's good, that's fine. What we will do is make it more like interactive. We'll try and make, lots, so just ask questions at any time. And hopefully, the more interactive this is and the more of a kind of group discussion, I think, with a smaller group is like you get more value that way. So anyway, I'm Greg, I'm co-founder and CEO at undo.io. We make time travel debugging stuff, and I'm going to talk in general about time travel debugging, which, I've spoken at these conferences for a long time, always steered kind of away from time travel debugging, so I didn't want to make anything kind of even, possibly marketing. But this is not going to be marketing, this is going to be detail. Anyway, just before we get going, if you do want to try some of this stuff out, and if my clicker would work, there we go. That QR code gets you into a raffle where we are giving away, I think it's 3 licenses of UDB. They're worth $7,900 each, so you get a single year for free if you win, if you're lucky enough to win the raffle. And the fact there aren't loads of people here just increases your chances, right? So it's all good. I'll show this up again at the end, but do take it now. But you can also try some of this stuff. There's open source stuff, there's stuff on different platforms. We'll talk about all the different kind of flavors. And we're going to get a lot into like how does it work? But before I get into any of that, just kind of want to kind of work out at the level of kind of where to pitch this. So I can just see, can I see a raise of hands? Who's used time travel debugging already? Okay, only 2, 3 people. And like, is that like just a little bit of how to play, or use it every day? Like what? Just a little bit how to play, a little bit, a little bit. Okay, so we've got 3 little bits, and everyone else not at all. So my mission today is to get all of you to go away and try it in the next, I don't know, week or something, right? If it's going to be the undo stuff that I work on, that's great, but I don't really mind, right? You can work on RR, you can take the Windows stuff. There's, my mission here is to get people to use it because it's really fucking good, right? It really, I mean that. Just this, it's amazing to me how, well, I hear it all the time. So it's quite hard for us to get new users to jump on the technology. When they do, it's super sticky, right? They never go back. And I've had several people now tell me that they find this stuff to be like heroin, which is not necessarily a quote we can use in our marketing, but yeah, one person, their license expired and they said, and then they used, I've got withdrawal symptoms, right? So it really, we had one of our customers, and again, I'm not making any of this specific to undo, this is time travel debugging in general, but I can tell you who it was because it's they're pretty open. They talk about this stuff openly with us. So this is SAP. This is the HANA team in SAP, right? So HANA, if you don't know, is this great big database at the heart of SAP. So probably every time you buy groceries or an airplane ticket or something, you're going to hit a HANA database somewhere in the world. So kind of mission critical, and it's big, right? It's millions of lines, many millions of lines of code, and does anything you could imagine. And they had a bug in that they knew it was there, and they could reproduce it very, very occasionally under load. And they were unable to fix it for 10 years. They got a time travel trace and they had it resolved in a matter of days at that point. And that's quite an extreme one, but it's not an uncommon story. Anyway, enough kind of talking about how great it is. You're gonna make your own minds up. You're all here, so that's a good start. Right, so this is the context, I think. I claim most programmers spend most of their time fixing bugs, I've said, but actually, or debugging. And debugging is like, actually, the most of that is finding what is root causing the issue, right? Finding what's gone wrong. I don't know about, you might well be all better programmers than I am, but if I'm working on something real, not just like a little toy example, how many lines of code can I write and have a reasonable expectation that it's going to work first time? I think it's like 10. Maybe, right? And how many lines of code can I change in an existing big complex project and have it work first time? That number definitely averages to less than 1, right? It just, we spend not much time typing and a lot of time figuring out what's going on. I know there's other stuff as meetings and design and review and all that stuff, but the lion's share is debugging, and we don't give it nearly enough attention, I think. And if you can't be a great programmer without being really good at debugging, and you can't be really good at debugging without making use of the various tools that are available to you. Okay, just to kind of set a bit of just what I want to kind of get everyone in the right kind of headspace for this, because I'm about to ask a horrible question. Here's an easier question. Cats or dogs? Show of hands for cats. Okay, dogs? It's kind of, actually, cats win. The cats have it there. Because they're better. Okay, I mean, you're entitled to your opinion, even when it's wrong. Yeah, all right, so I want you to make, debugger or print statements, okay? You've got to choose one. The point of this cats and dogs thing is to get you off the fence, because everyone goes, oh, it depends. You're not allowed to say it depends. So I want, who prefers using the debugger? And print statements? Okay, debuggers definitely win that one. That's usually more of a 50-50 split. I guess we've got a massive sample bias because of like the title of this talk, right? Why? You put your hand up, Roger, very definitely.
I don't like the word debugger. Mm-hmm. Unfortunately, I can't find a short word for it. Interactive visualizer.
Yeah, okay, yes, yes.
Sync time manually when you use an interactive visualizer.
Uh-huh.
Print statement, you put it in the code once, and then it's there every time you debug the problem.
Right. So if you have to like run it, because you've got print statements kind of conditional, they'll come out and you can turn your log level up and down and turn things off and on. Yeah. Right, someone who said debugger. Maybe you put your hands up because you wanted to please me, right? Because I'm here talking this stuff. But can I hear? Let me hear somebody talking why the debugger is better than print statements. Someone put their hand up. God, it's a small crowd. Come on, you can do it. Oh, that means everyone just did it to please me. Yes.
I suppose you can also print statements in debuggers.
You can put print statements in debuggers, yeah.
You can do more.
Right, so you've got like a superset of functionality.
Yeah.
So, yes. Watchpoints, yeah, watchpoints are completely awesome, right? Yeah. Anyone who's used watchpoints at least at some point? Really, almost everybody. But a few haven't. So watchpoints, they're called in Microsoft, in Visual Studio, they're called data breakpoints. And kind of what it sounds like, right? So you run the program until some watched piece of data changes. I think that the thing that, so having just told you have to get off the fence and choose one, I'm going to say they both suck, right? And they both suck for different reasons, obviously. So print statements, well, the obvious thing is you have to recompile the code to add new print statements, and you have to run it again to find out new stuff. And any decent-sized program is doing, I mean, the state space of even a moderately sized program is enormous. Billions of things every second. You know, maybe you don't have millions of lines of code, but still lots of lines of code. And you can't print it all. That would be completely, beyond impractical. So you have to print certain selected things, and you have to choose what to print kind of ahead of time. And if you didn't print the right thing, then when the program runs, you don't see the bit of information that you need. And so you tend to go, oh, right, now I need to add another print. And you go in this endless cycle, add a print statement, run again, add a print. Well, it's not endless, but unpredictable number of times around that loop. So basically what this means is we can't get more information out of our program without changing the program, without adding stuff to the program. And that's a major drawback. What you want is tight feedback loops, so you can ask questions and get answers very quickly. Debuggers, on the other hand, do that. They let you just, think anything you can think of, any question you can think of to ask your program. You can just ask, what's this value of this variable, or look at this data structure, or whatever it is. But debuggers, at least if they're not time travel, don't tell you what you really need to know, which is what happened. I'm going to get into that. And I'm getting ahead of myself on the slides here. So here's another way of talking about why both suck in different ways. So you've probably seen this old XKCD cartoon. They're goofing off in the office because their code's compiling. Why is it compiling? Because they added a printf, right? Probably. I haven't got stats on how many rebuilds are because someone added a printf, but I bet it's well over 90%. Then there's this cartoon here from Monkey User. Everyone's probably been there. Step, step, step. Oh, we stepped too far. Start again. And I just like the way the future him is pulling back and but actually, that's not that cartoon there is not really the point for me. And I was discussing a little when we put these slides together. I was discussing this with our CTO as like whether that's a good thing to have or not. I don't. In some ways, I don't like that cartoon because I think it misses the point of time travel debugging, because it kind of like, yeah, it's nice that that doesn't happen anymore. That'll never, once you pick up time travel debugger, that will never happen to you again, and that's undoubtedly a good thing. But that's not the point, right? That's like that's a tiny, that's 1%, 10% at most of the story. You probably know this quote. Lots of people do. Brian Kernighan. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can when you write it, how will you ever debug it? And I think pretty clearly what Kernighan meant here when he said this is leave yourself margin for error. You're probably not quite as smart as you think you are. I've had another metaphor that I quite like, is it's like, not that I even remotely brave enough to ride a motorbike, but someone saying people who've ridden motorbikes for a long time, they give themselves lots of margin for error. The young, full of testosterone, 20-something lad is racing around. He's a much less skilled motorcyclist than the older person, but goes much faster, takes more risk, and the more experienced, seasoned programmers know that this will going to end in tears if they try and push things to the edge. But I think there's an interesting, but nonetheless, there's an interesting, I think, kind of corollary consequence of what Kernighan is saying here, which is that debuggability is the limiting factor on how good our code can be, right? Whatever your metric for good is, whether it's how fast it runs, how small it is, how maintainable it is, how quickly I can write it, whatever your metric for good is, if you're able to debug it twice as better, you can make your code twice as good. So being really good at debugging is not about just being really good at debugging, it's about making better code. So there's lots of tools and things out there for debugging, and I'm just going to kind of name check them. I don't mind. We've got time, so if we want to get into some discussion on this, any of this stuff, I'm very happy to. But for now, I just name check them. So what I've called dynamic checkers, right? Valgrind, address sanitizer, those kind of things. Who uses these at least sometimes? Everybody. Okay, who uses them like all the time? Yeah. Okay. All right. 2, 3. Yeah. I mean, yeah. I mean, we certainly do. We have in our CI, when before you can merge your branch, it has to run a bunch of tests that run with Valgrind and undefined behavior, UBSAN, which is kind of a superset of address sanitizer. Yeah, why not, right? I mean, they run a little bit slowly, but human time is expensive, computer time is cheap. So these are good things. The debugger, we just talked about that. I mean, yeah, whatever, depending on what language or platform you're on, use your debugger. There's some kind of cool dynamic logging stuff out there now. There's some cool stuff like Lightrun, which is like printf but better. But yeah, mostly it's just printf, right? That's what most of us do most of the time. And because what print gives you that debuggers don't is a view of what happened, right? Past tense. Gives you a story of my program's execution. And when you're debugging, that's what you're thinking, right? How did that happen? Obviously, I didn't expect the code to do that. I didn't expect that assertion to fire, obviously. Otherwise, I wouldn't have written it, right? It shouldn't. So something happened. Something happened that I wasn't expecting, right? I don't mean how did that happen? Or how did that happen? What I mean is, when we run the program, we've got a set of expectations of what's going to happen. And reality often diverges from those expectations. And so the job of debugging, root causing, is like, where is that point, right? Where does reality diverge from my expectations? And of course, it's normally more like that. And this is a totally non-trivial question to ask, because the computer's doing billions of things every second. I've got millions of lines of code. I'm looking like it's the ultimate needle in a haystack challenge. Which one of those billions and billions of operations was the one that I didn't expect, which is the one that's wrong? So what I tend to do for all, but sometimes it's easy, right? Sometimes the program crashes. You load up a core file, and it's like, oh yeah, I dereferenced some pointer that was null, and it's allowed to be null, and I forgot to add the check, so fix it. Or sometimes I get a log, and I can just look at the logs, and I can think really hard, and I can just figure it out. But often not. Often I'm just missing that piece of information. So what I need to do is rerun the program every time, getting another clue, getting another piece of the jigsaw puzzle until eventually, jigsaw puzzle, it's a bit of a weird jigsaw puzzle because it's one where there's a magic piece and you put this magic piece in and then suddenly the whole thing sort of falls into place, but you don't know which one, which is going to be, I need a better metaphor. Maybe it's like with clues, we're looking for clues in some sort of detective story. So every time I run the program, I add another printf, I get some more information, I get another clue. And ultimately, sometimes it goes a bit like that, rather than Sherlock Holmes. But, right, so this is the point I'm trying to make. It's about what happened past tense. And that's the thing with time travel debuggers, and we'll get into it. I'll show you a demo, and we'll talk all about it more in just a moment, but I just want to set this context, right? It's not about, stepped forward too many times, so now I can just go back. It's now I can ask questions not just about the current program state, but what happened and how I got to that state. And where was that divergence from my expectations? So I think another thing I think a lot about bugs, obviously. One of the things, I think there's two things actually mainly. I'd be interested to hear if anybody's got any other views on this, and maybe add some things in, but I want to get it on a 2D chart. But I think the two main things are the time that elapses between the bug itself, between that bad line of code running and you noticing, right? The longer that is, the harder it is. That's why that example I gave before of forgot to check for null is really easy, because the program crashes right where I forgot to check it. And that's why the worst is always bad results. The program ran to the end and gave me something, gave me a bad output. That is always the worst. And sometimes, it depends what your program is, but that can be days in the worst case scenario, but it can always be, always going to be a long time in computer speak. So it's also, by the way, why assertions are such a good thing, because what assertions do is narrow that time, right? And then the other sort of vector axis is how deterministic is it, right? So when I'm rerunning it and I'm getting that other jigsaw puzzle, that other clue every time, if the program always does the same thing, well, it might be painful. I might have to run it a bunch of times, but at least I'm going to get there in the end. But if it does a different thing every time, maybe it only fails 1 in 1,000, but maybe worst of all, it fails in a different way each time, then every time I try and get another clue, it's another murder scene, right? Or another jigsaw puzzle I've got a piece for. And it's like, well, congratulations, I've now got 100 jigsaw puzzle pieces, all for different jigsaw puzzles. Like, good luck. And of course, it gets really fun when we're up here in the top right-hand corner when we've got both of these things, right? Those are the bugs that can take literally years to fix. Or everyone's favorite, the Heisenbug. Add a print statement, or attach the debugger, and the bug goes away. So with time travel, we can kind of get the best of both these worlds, right? We can ask questions about what happened. I like this image for time travel, the H.G. Wells time traveler, because rather than the kind of more modern ones, partly because I just think it's a bit cooler, but also because he's more like, unlike a lot of the more modern kind of sci-fi stories, they go and change time, change history. He's more of an observer. And that's what we're talking about with time travel, right? We're not talking about going back in time and changing the course of events. We're talking about just going back and seeing exactly what happened, right? Back and forth. So only a small number of people in the audience have tried time travel debugging, and they've only played with it. So let's run a demo so we can know what we're talking about. So, right, last time I did a talk, I did the demo using VS Code, and then Anastasia was very sad. So now we're going to do it with C-Line. Let's run this again. Oh yeah, isn't it? Okay, let's try and make it bigger. Then now C-Line has C-Line has a really neat presenter mode. If I can, anyone remember how to do that? View. Appearance. Here we go. This is one of the nice things about it. Oh, except now I need to figure out how to get my. Show me my debug.
Do you think you could change the theme to lighter themes?
I could certainly try. Navigation. Anyone know the way around Sea Lion?
Okay. Okay, don't worry about it.
Never mind. Yeah, let me see. First of all, let me just see if I need to, because I've put it in presenter mode, but now all the debug buttons have gone. View. There we go. Right. That's what I want. Okay, I think this will do it. So it's a little bit cluttered, but at least this thing's nice and big. The details of this code don't actually matter that much. It's just more the flow that I want to show you. So here we are in the debugger, but I've got these extra buttons here, right? So go back in time. These are like so this is step over, step into, step out. These are the inverse of that. So let's just resume my little program here. And got an assertion fail. We can see, sorry, this screen's really cluttered here, but I can see, okay, this is in thread number 2. I've got lots of threads here, but we're in the second thread. We've got an assertion failure because this thing's square root cache is 0, and it ought to have been 15. Can look at the code here. So we've got, it's calling square root, and so it looks like, and then before that's called this cache calculate. It's passed in number, which is 255, and it's returned a result of 0, and it looks like it should be returning the square root, and obviously 0 is not the square root of 255. If I had a call file, I could have done all of this, right? I can look up a call stack, I can see who called me, but that's the only exception, actually, where non-time travel debuggers do give you a little bit about what happened, because they give you a call stack. And that's one of the most useful things, I think, actually. Most used things in debuggers is to look at the call stack, because that's the best they can do at telling you what happened. But obviously, like, it's a sliver of the program execution. It's a tiny bit of what happened. And if I was looking at a core file here rather than a time travel session, then that's it. All I know is cache calculate returned the wrong value, and I have no idea why. And that information is like gone from the universe, right? But you won't be surprised to know this is time travel. Now, actually, you can see if you, maybe I can just make this slightly bigger. So we're not actually in the assert function. So assert, like actually, there's a call stack here. It calls down to a bunch of assembly code, or code that I don't have, libc code that I don't have debug info for here. That's fine. So most time travel debuggers work just fine without having any debug information. I mean, say just fine. You can't like get the you can't see the source, but like say you can rewind through time. So let's pop up the call stack. So I can do that with this. So this is, whoops, no, this one. So this is reverse step out. So this is like uncall. So here I am deep inside libc. C-Line's sort of helpfully hiding it for me. But if I come out a bit, we'll come out a bunch of function calls. One more. There we are. Right, now I really am here. So 0 is not equal to 255. So now I'm nearly at the end of my program, but not quite. So why did cache calculate return the wrong thing? How did that happen? So let's just step back. So here's the first bit of kind of obviously magic that you won't ever have seen if you haven't done time travel debugging. Step. And ooh, we've gone back one line rather than forwards line now. Now I'm going to reverse step into, and we'll go into cache calculate, and we can see what it returned and why. So it returned 0. Okay, I've got some threads going on here. So maybe this is a race condition, right? Maybe this is like a locking problem or something like that. So let's just go back. I'm going to go back to before this mutex was unlocked. Well, what I'm showing you here is a bit of like how you do have to think differently a little bit when you're doing this. So I'm going to go back in time to before the mutex was unlocked. So that means the mutex will be now locked, and maybe things will look different. So we go back. By the way, as I go back, all the data here is all changing, right? Let's get rid of that because that's a bit of a spoiler alert. So we're not just seeing the lines of code that have executed, we're unwinding the full program state. It's basically, it's kind of like, it's almost like when you've got a core file or a memory dump, I think they call them in Windows land, you've got a snapshot of the complete program state at a single point in time. When you've got time travel, it's like having a core file for every single instruction that executed. You can see all of it for any point in time, which is obviously a mind-blowing amount of data and just isn't going to scale. And so we'll get into like how this is implemented in a way that really does scale in just a moment. Right, anyway, I distracted myself. So we're going back one more line. So now this is the beginning of this line. So now this is before the mutex was unlocked. Let's have a look at things. Oh, well, it's like all looking very much the same, actually. So I don't think it was that. But I'm getting it out of this cache. What's this cache? Let's have a look. By the way, I'm sort of pretending I don't know what this code does, because another really good use case for this, as well as debugging, is just understanding what does this code do. I've been asked to work on some really complex, big piece of code, and I've got no idea what it did. The person who wrote the code has left the company. Yeah, so the only thing is I need more pixels. Hang on a second. I'll come down in a minute. So let's have a look at this Gcache. So yeah, so it's telling me that the square root of 255 is 0. So classic bad day at the office, right? My cache contains bad data, and it tells me the square root of 255 is 0, and I've got no idea how that happened, right? How did that come to pass? Maybe it's a pointer error, maybe it's a threading problem, maybe it's a logic error. I mean, I don't know. So let's add a watch point. And that is going to happen. Oh, there it is. Right. So add a watch point. So I'm going to watch that expression. Actually, sorry, I don't want to do that. I want to go. I'm going to watch. I just realized I'm not quite sure what C line's going to do if I do that. So I'm just going to play it a bit safe and watch the first entry, or the 1th entry in the cache. So add the watch point. And now I'm going to go back in time. So yes, you said watch points were cool, and watch points are kind of cool when you're going forwards. They're completely awesome when you have the ability to go back in time. Because when in a moment I hit this reverse button here, what's going to happen is we're going to go back in time to the moment that data I just watched changes. That is how that happened. That is how the cow got the toy car on its head, right? So, boom. So I've gone back in time. I've gone back. Oh, no, I haven't. You know what I've done? Because I'm watching that I value, I think. Damn it. Okay, hang on a second. I might have to give up using C-line, because the C-line is defeating me. View notes. Tool. View. I think I accidentally added that. What I think I've done here, just to explain it, is I've added, I thought so. So I added 2 watch points, one for the first entry, the 1th entry in that array, and in that array, and the other for the ith entry. So then I went back in time to when I changed, and so the value of that expression has changed and it stopped. I didn't want to actually set that watch point. So let me get rid of that. This is the other nice thing. let's pretend I did this on purpose to show you that when you're doing time travel debugging, when you get a bit lost and a bit confused, it's a lot better. And generally, we can just keep on trucking. Right, let's try again. So reverse, resume. Okay, that's what I was expecting. So now I've gone back in time until that entry in the cache last got updated, right? And actually, if let's just move this up a little bit, and then we can have a look here. It's actually midway through updating this, so let's go back one more line. This is another sort of cool thing you can do here. So we can start to, I think I know what I'm beginning to think I know what I'm seeing, but let me just step back and forth and make sure I really am seeing what I think I'm seeing, because that's always the worst thing. One of the many bad things when you're debugging is you kind of think you've got a clue, but it was a red herring, right? And you spend time under false. So let's make sure. So here's that first entry in the cache telling me the square root of 112 is 10, which with integers is correct, right? This is integer arithmetic. Let's have a look at the threads. I'm now in thread number 6, so we've gone back to a different thread, but okay, interesting. So it was another thread that... Now, watch the data here when I step forwards. I'm going to step forwards to these 2 lines. I'm going to watch that data, and that is like sort of live action replay on Match the Day or something, right? So step, step. That's it. Look, it just changed 255 to 0. That's the smoking gun. Now I'm starting to get close. So what's going on? Well, number adjacent is -1. Okay, so I've got some sort of overflow here. And so the square root is nonsense. I tried to take the square root of -1. Well, why is number adjacent -1? What's going on here? Well, actually now it's getting close enough that I could do this by code inspection. But this is a demo. I'm gonna... Oh, I don't know what an inline watch is. Why is it asking me that? Let's see what happens. God, this is me using C-line, unfamiliar with it. No, okay, ignore that. Right, so number adjacent is -1, and I can see it's being set here. Number adjacent is being set to number -1, and number here is 0. So this is a tiny program. This is less than 100 lines of code, but actually that's a non-trivial bug. And I've done a number of times, I've asked people to see if they can just stare at the code and figure it out. And I mean, I guess if you gave someone long enough, they would. But in a forum like this, at least nobody did. So that's cool, right? That's clearly very cool. Let me go back to my slides. No, before I go back to slides, let's just pause for questions. So what, or just reactions? Is that what you expected? Nodding, that's what we hoped time travel, for all the people who never use it, that's what we hoped it would be. On a scale of 0 to 10, and like, that seems really important. Not being nice to me, honestly, what do we feel? Like, is that okay? It's a neat trick, or is it like, holy shit, that changes everything? More on the holy shit end, right? Yeah. Does it scale, right? And that's the thing. And that's what we're going to get into in the second section of this talk. Does it scale? And the answer is, it depends how it's implemented. So, and in fact, this time travel thing, like it's not in and of itself a new idea. There are papers going back to the 1970s, I think, talking about this stuff. There have been countless PhDs to try and implement it, and people doing things, people even making specialized languages that will allow them to do it. What's changed in the last few years is a number of technologies, a number of implementations have come along which do scale, and which scale to, in some cases, up to, well, pretty much the biggest programs imaginable, right? I mean, there are people using this. There will be people using this right now on programs that are way bigger than what you work on, right? I assert boldly. But I mean, I know people running on some of the biggest programs I know are the EDA tools, right? So the stuff where chip designers write their chip in Verilog, and then that goes through these tools, and it gets through a bunch of tools, it gets turned into a kind of transistor design, and then that gets sent off to TSMC or whatever, and they make a chip out of it. Those bits of software are big, right? They are like terabytes of working set, and they run for days. And they use time travel all the time. There's also people who are doing lots of very complex distributed systems, right? With lots of processes, ephemeral coming and going. It's super valuable there as well. Yeah, so. Clicker, here we go. I'm gonna come back to this, and like especially if we have time, but I'm gonna get back into the, I'll come back to all this. So yeah, the question was, does it scale? Remind me to go back to those other slides. As long as we get time, I'll probably forget. This is a screenshot of the omniscient debugger. You can see at the top, and you can see a date, actually, 2006. This was my first exposure to this concept. A friend of mine showed me this YouTube video of somebody doing this in, this is Java. This is a Java debugger. Because everyone, that's what everyone used in 2006. And yeah, I saw this thing and I was immediately like, yeah, my mind is blown. Like definitely, holy shit, this changes everything. But it's kind of easy with Java, right? You can see how you would implement this in Java. And even in Java, does it scale, right? Some Java programs are really big. This was done by a professor at, I can't remember which, somewhere around Boston, one of those universities. And, you know, for the students doing, you know, CS 101, worked really well. But yeah, this didn't really scale. Let's get into why. So what happened, okay? That's the question we're trying to answer here. Another way of saying that, a more kind of computer science-y way of saying that, is what was the previous state, or what were the prior states that led to what I'm currently seeing? And so, yeah, capturing the trace of execution is one thing, but all that data, right? So what am I going to do? So I'm either going to save it or I'm going to recompute it. Those are my two options, right? Now, saving it, that's what the omniscient debugger did. That's what most of the implementations of this stuff did until, you know, sort of a few years ago. And they would just save. Now, obviously, I'm not going to save a complete, I said before, it's like a core file of every, you know, a core file per instruction, which would just be bananas. And even the most naive, non-scalable implementations don't try and do that. You don't try and save the complete program state for every instruction that executes. Even for a student project, that's not going to work. So obviously what I'm going to do is just like store just the deltas, a little bit like an MPEG encoding type thing, right? I'm just going to save what changed. But even that does not scale, right? Quite spectacularly, because I'm running billions of operations every second, and every one of those, think about it, every one of those has to change something. If I issue an instruction on the CPU and it doesn't change registers or memory or anything, then I'm live locked. I'm going to go back around, you know, it's not going to make any, it has to jump to itself. That's a tight loop live lock. So every instruction is going to change something, and that's going to be like an 8-byte record or something, and that's going to be an 8-byte record for billions of these things every second. So that does not scale. So what about recomputing it? Well, problem is, if a statement's like this, obviously I can reverse that statement. That's an inherently reversible statement. If I know what A is, after that's executed, I can deduce what it was before it executed. But I can't that, right? Once I've done that assignment, A equals B, obviously A and B are both going to have the same value, and I don't know what value A was prior. So I can't run backwards, right? It's not something that computers do. Actually, there is an interesting line of research making reversible logic, mainly around, that's based mainly around actually energy efficiency. So it turns out that there's some kind of, I'm well out of my depth here, but it turns out there's some kind of E equals mc squared kind of equivalent for information, and destroying and creating information takes a certain amount of energy. And so they've worked out they make this reversible logic, it can use less energy because information isn't being destroyed in the same way. Anyway, that's like proper, you know, that's certainly not available to buy hardware, not going to be anytime soon. So for what we think of computers, they're basically not reversible. So I can't just run it backwards. So instead, what I'm going to do, what I can do is re-execute it, right? So what happens is you get a series of snapshots, and when in that demo I did a reverse next, what was happening under the hood is it went back, found the most recent snapshot, and played that forward to just before where I was. And then it reconstructs all of the program state. This is much, much more efficient. And it's why, like counterintuitively, so I said it's a core file for every instruction that executes. So often a recording is smaller than a core file, than a single core file. Because you kind of start off with lots of zeros, and then lots of processing happens, and then lots of non-zeros ends up in your program state. And if you just rerun it, you can recompute it, okay? As long as the program does the same thing every time. And I talked before about that sort of those two axes of what makes bugs hard and hard bugs. These are just not interesting if it only works on completely trivial, reproducible, deterministic issues. So what we have to do is this the event? Yeah, capture. Sorry, these diagrams aren't great, but just something to talk to. It's better just to explain it. Capture the non-deterministic inputs to the program as it's running the first time round. And then when we're picking up one of those snapshots and running it forward, we don't let it do anything that's non-deterministic. We reconstruct, we synthesize the results. So most things, like turns out 99.99% of what the computer does is deterministic. A equals B, A++, all these things are completely deterministic. If I just do some maths and I give it the same inputs, it better yield the same outputs. Floating point weirdness, let's not get into that, but most of it will just be like it's predictable is another way of saying it from deterministic, right? So what things aren't deterministic? System calls, yeah. That's a big one, right? I mean, so get time of day, get PID, anything is liable to give you a different result. And if, in fact, if it wouldn't, then it shouldn't be a system call. It should be a library implementation, right? The system call is like reaching outside of my process and getting something from the outside world and influencing it. So every system call is unpredictable based on the state of my program at the time it's done. What else? Multi-threading, right? So the ordering, if I've got two threads running, both accessing the same bit of memory, the ordering with which those accesses happen is not guaranteed and will be different times I run it. Yeah. User input, but I'm going to say that's system calls, right? So no, we're still at 2. Depends how you define starting state. I'm defining the starting state as the things have been loaded. Now, but when I call DL open or whatever and load a dynamic library, that will, the operating system these days will deliberately put it at an unpredictable place, but that's a system call. So I've already handled that. Shared memory, yes. So most memory holds this property that when I read from it, what I read back is what I most recently wrote. Shared memory doesn't. So shared memory here, when I say shared memory, I'm kind of including, could be 2 processes have some shared memory between them. It might be shared with the system, might be shared with the operating system, might be asynchronously receiving data into some buffer, might be shared with the hardware, right? It might have some sort of RDMA type hardware and it's just DMAing straight into. So, but that's all, yeah, so shared memory. So what did we say? System calls, thread switches, shared memory. There's 2 more. Some instructions, yes. Give me an example. RDTSC, right. Every time I do RDTSC, I mean, unless I'm running the entire thing completely deterministically, it gives me a different result. Yeah, and these days there's like, get me a random number instructions, right? And maybe if you want to be really pedantic, system calls are an example of non-deterministic instructions. So I'm kind of back to 3 because there's always a syscall instruction of some variety. I'm going to keep them, they're kind of separate, so I'm going to keep them as 4. One more. I'm talking about Unix type systems. There's possibly others in other systems, but one more. Signals, yes. Asynchronous signals in particular. So some signals are deterministic, segv, because I did an invalid access. Yeah, fine, that'll just do the same thing every time. But if someone fires sig user 1 at me or sig alarm goes off, that's not a But that's it, right? On a Unix system, on Linux, those are your only 5 sources of non-determinism. And so if we can just capture all of those, we can pull this off. Easy, right? This leads on to a thing that I thought was quite interesting. So I'm talking here about non-determinism at the process level, right? And it turns out the process boundary is the right place to do this. So, inside my process, I've perhaps got, probably got my C library. I might have whatever libraries I've got. All these libraries live inside the process, right? It's the Unix process. That's the level we're talking about. That's what has these properties of system calls and thread switches and shared memory and stuff being unpredictable, but everything else being predictable. We can record multiple processes at the same time. That's fine, but they then make multiple recordings. So I'm recording at the process level, the address space level, really, because that's mostly what I kind of care about. Now, interestingly, yeah, we'll come back. We are going to, right. So, yeah, so we just covered this. We invented this ourselves. That's great. What the hell was I doing my time for the last 10 years? So yeah, so the big design, so there's some design decisions about how we implement this, and there are different implementations and they have different trade-offs between them. So I'll get into that a little bit. So at what boundary to capture? I'm going to go slightly out of order with my slides, I think here. So yeah, at the kind of, because I could do it at a finer grain, right? And that original thing I showed you, that Java Omniscient debugger did just that. That captured it, they did it at the JVM level, and I did some interesting, clever, JVM gave you some hooks that you could capture stuff, and that was quite neat because it meant that you could be very localized. You could say, I just want to record this class or this method execution, or even these few lines, and everything else can just not be recorded. But the trouble is, for those really nasty bugs, actually most bugs, you don't want to. Now you're back in printf land. Now I have to know what to record. Much better if I can just record everything. And you get into this problem of it not scaling, right? This thing I was talking about, like every instruction being essentially a diff that I need to store, so gigabytes and gigabytes per second. And even, so basically everything, apart from this omniscient debugger, which kind of didn't scale, everything's ended up doing at the process level. So, I shouldn't have gone out of order, sorry, because I want to talk about the different, let's just talk about the different ones that are available, because otherwise I just realized I actually knew what I was doing when I set the order of these slides. Who knew? Actually, but I'm going to skip that for now. Right, so stuff that's out there. So obviously there's the undo stuff that everybody should definitely buy. RR stands for record and replay. It's really good. It's open source. You can just download it and use it. Where it works really well. We'll get into a bit of like what the different, like where they work and where they don't. So the people who said they've tried it a little bit. So who's used RR? 1, 2, right. Everyone else, what the fuck are you doing? Get out, and it's just there, right? You can just go sudo apt install or whatever your package manager is. It's just there. I'm going to show you how easy it is. I wasn't planning to do this, but like, people often assume that RR is our competition, and like, really, no, printf is our competition. This was the program I just showed you, so is this good? This is probably, so the problem with RR is it's a little bit finicky about where it will run, but and I've just upgraded my laptop, so this, anyway, let's see if I can get this to work. So it was that, and I need thread. So if I run, this is the program I showed you before, right? Does that called up? So this, I think I've downloaded RR. Does that work? Yeah. So no. Okay. So it's all right. We can do this. We can do this. So it does need these perf events, and if we have time, I'll get into why. So I'm going to echo 1 into sudo Hang on. How do I? Oh. I do know how to do that, Bash, but I can't even type my password live, let alone do that. So if we do that, this I think now should work. Yeah. So there we go. So you can see it ran a little bit more slowly, but just basically works. And that was to record it. Now I can replay it. If I just say RR replay, it will replay the most recent recording that it made, which will be this thing. I can put a breakpoint at main. I can continue. Let's go into TUI mode. Looks like that's better. Continue. Here's my back. So like you can like just works, right? So you can, and if your computer isn't too new, you can just go sudo apt install RR. You don't even have to bother about building it from source. Yeah, this has got a newer CPU that confused RR a little bit, so I had to hack it. But they're always catching up, so just don't use too new hardware. So that's RR. GDB has inbuilt time travel. They call it process record. I said it works-ish because it is. Let's just see what that looks like. Now the GDB one, this is not scalable. This is the record every instruction. So I'll go start. So you just type record, and now it's recording. Now I continue. Remember, if I ran natively, it ran in like a, I don't know, hard to measure time. You know, looked like 0.1 of a second. When I ran it with RR, it ran in what looked like, I don't know, half a second or something. Similar kind of with undo. Oh, okay, it doesn't even like the system call that, so it didn't even work. But if it didn't barf because it hit a system call it didn't know about, then it takes, I think I timed it, I think this program takes hours and hours and hours to run under GDB process record. So GDB has inbuilt support for time travel, but not really, right? It's kind of useful for having a play. Maybe if I've got a few lines that are like really baffling me and I want to figure out how is, like someone's been really clever with some optimized loop or something and I want to figure out how it works, it might work there. People do use it, security researchers will use it a bit when they've just got like a binary and they're trying to work out, they haven't got source code and they're trying to see how things fit together. But it's very, very limited. It doesn't really, it's not, let's not talk about it anymore, it doesn't really work. But RR totally does work as long as your program is within and your system is within what it will tolerate. Windows, TTD, Microsoft always just use TLAs for everything because they seem to be completely unimaginative and all that stuff. So Microsoft Time Travel Debugger, TTD. And if you're an embedded person, you've got there's two main ones, the Lauterbach and the Green Hills Time Machine. And they basically, as long as your CPU supports it, you need the embedded trace macro cell. And then these work at the hardware level. So they're not, I mean, they're super fast and they work on bare metal without an operating system. But they're very expensive and you need to have like your JTAG port and stuff, but they're very cool. Now, I never quite know. I think, we're the Association of C and C++ users, but other languages are allowed, right? I think in this conference. So yeah, there are other languages. Actually, so JavaScript, React, they have this thing called replay.io. It's quite cool. They're quite a new company. They came out of some people. Actually, Mozilla is an interesting place, right? Because Rust came out of Mozilla. RR came out of Mozilla, and the people who did that sort of left and started a company on their own. And this JavaScript replay.io, that came from some Mozilla folk, and they've started a company doing that for, so I think when we say our other languages are allowed, I assume that that doesn't include JavaScript. But oh, so many reasons. But yeah, obviously it's a very important language. There's lots of it out there, and web developers have a really hard time with users saying, "Oh, it didn't work very well," and they're really bad at giving them bug reports and stuff. So they can record the your browser session, but not session recording, which is recording the screen. They can record it at the kind of, then you can debug it just like I showed you, but in actually kind of nice inside the browser debug tools. .NET, yeah. So that's Microsoft Visual Studio will debug .NET with time travel debugging. There's a company called RevDebug who are doing it as well. You can do it with Java. We'll happily let you debug your Java program through IntelliJ. Yeah, Rust, Go. Also works with both RR and undo. So pretty good coverage. I'm sure there are others, but whose favorite language is missing here? Or maybe not favorite, but they're cursed to use. Python, right. We kind of support Python now. Like it's a bit, what's the right word here? Yeah, you know what I'm saying, right? But it actually works. It's useful. It says, but it's not seamless, kind of, oh, here's nice Python debug and get like your PyCharm thing and step through with the debugger and see it all beautifully. We haven't done that yet. So it's a bit hacky, maybe that's the right word, but totally works. And you can record your Python program and see where you were, and because you can kind of, it's through the GDB Python interface. Anyway, yeah, so Python mostly needs a bit of polish. That's it. That's all the languages, right? No one, right? Fortran works. We have customers using Fortran through the GDB support for Fortran. You can even do it with COBOL. I'm surprised it hasn't taken off more with COBOL. Actually, we did some work with Micro Focus, who makes this kind of COBOL thing, and because all the COBOL programmers are like all the people who wrote that code. Well, the lucky ones are retired, right, and the unlucky ones are dead. The really unlucky ones are now trying to work out how all this COBOL works, right? And now the laws changed and the tax rules have changed and we've got to change it. I thought, anyway, I think it turns out it's hard to get COBOL programmers to adopt new technologies. I think that was the problem there. It's more of a personality, psychology thing. Yeah, right. So, works for all the languages. And what happened? So what I thought was quite interesting is, like, even replay.io, and I haven't put it here, but the Visual Studio time travel debugging of .NET, they still work at the process boundary. That turns out to be the place to do this. What the replay.io folks ended up doing, they first started to do it at the JavaScript engine level. Let's make JavaScript be just kind of time travelable. And they in the end, they gave up and they forked Firefox and then later Chrome. And they made, but when you take a recording for replay.io, you actually record the whole browser. They record the whole browser. The JavaScript developer, of course, doesn't see that. They just see, you know, whatever it was doing at that particular point in the JavaScript. And that turns out to be, that's exactly how we do it with Java. I like the, you know, was it totally different? I like the phrase that Java is to JavaScript as car is to carpet. You just start with the same letters, but still, yeah, our Java support, we record the whole process. So the way this is working at its process level, like, it doesn't matter whether it's written in C++ or Java or handcrafted assembly, it's just instructions and system calls at the end of the day, right? But then obviously what you want to do for the Java programmer or JavaScript or whatever, when you're rewinding time, you need to kind of stop at exactly the right point so that it's at the model of where your Java program is, or JavaScript program is. And there's some particular challenges with doing that for Java, because Java's kind of made to be debuggable. The JVM has this interface, JTB, I don't know, something, and you just connect a socket and it will kind of give you all the debug info. And it's kind of they've deliberately made it easy to attach debuggers to a Java program. And they said that, oh, but if you're going to put a breakpoint anywhere on in the Java program, including single stepping, as a kind of special case of breakpoint, then we're just going to run that code not JITted. We're going to run that code in interpretive mode, right? Because it doesn't matter about performance. You've got a breakpoint. You're going to hit a breakpoint. It doesn't matter if it's going fast. And obviously, you know which functions have which lines of codes can have a breakpoint on before you execute it, right? We don't with time travel. So that was a real pain to implement. What we ended up doing is, but they were thoughtful enough to give, Java has this notion of safe points, which is when the garbage collector can run. So it's kind of hairy, but it works. So what we do is, when we're replaying one of our recordings, at a safe point, we fork a copy of the process, and then if there's a breakpoint coming up, if there's a breakpoint on the method we're now executing, and then we just have a really noddy JVM implementation, which are easy to do, which runs to the point in question in interpreted mode from that forked process. So it's kind of hairy. It was hard to get to work, but does work. But still, yeah, you want to be at the process level because it is just too hard. There's not enough guarantees about like, yeah, this module doesn't talk to that module, but oh no, someone returned a pointer to a structure that it then updates asynchronously or whatever. And likewise with the Windows.NET, see again, they have to run on the CLR. They could have done it. They could have made the CLR reversible, but they didn't. They did it at the process level. So that's what boundary to capture. The other perhaps big decision is whether to do binary instruction rewriting. Pros and cons. Main con being it's hard, and can be slow, although it doesn't have to be slow. You can make this pretty quick. So undo does binary rewriting. The Windows WinDebug TTD does binary rewriting. The others do not. So this is like, it's a bit like the way that Valgrind works, right? So it's just we translate the code from the source machine code into another machine code, which is like a functionally identical, but has enough for us to get our fingers in. You need to do this, or well, if you don't do this, you need to solve it another way for a couple of reasons. One is, Roger, you mentioned signals as one of the, you identified signals as one of the non-deterministic things. So when I'm rerunning my program, sig alarm comes in at some point. Okay, so actually so the big downside with doing this at the process level in this replay, the advantage of doing it in the replay mode is like this re-execution, is it's the only way it's going to work, right? It's the only option you have, but it is really hard to get right. Because if you just get it slightly wrong at replay, you just miss one little bit, then there's kind of an irony. These systems are super hard to debug, right? You know, I said with the axis of like long time from the bug to you noticing and non-deterministic, like, we have loads of these, right? There was a real kind of inception point when we could eat our own dog food and debug our own product with our own debugger, because then you could like, actually work through these problems. But it's hard to get right, but it's anything that will work. Anyway, when you're doing that, when you're replaying and your sig alarm comes in, you have to replay it at exactly the right time, exactly the time it came in the first time. Otherwise, you're going to get these really subtle differences, and things are going to just go badly wrong. You're going to get these divergence when you replay. The other reason, though, is that's perhaps a little less obvious, but just as important, is at least if I want to enable reverse step functionality, so I'm stepping backwards through my loop. My loop's iterated like 100 times. Now I want to step back one iteration. Well, I need to replay. I can't just put a breakpoint there and replay it, because that'll be the first iteration. So I need to iterate exactly the same. Well, if I've done 100 iterations of my loop, and I need to be exactly 100 iterations before I stop one instruction earlier, unless I'm at the top of the loop, then it needs to be exactly 999 iterations, right? So when I replay, I've got to stop at exactly the right time. So I need to know what time it is, timing, how much program execution has happened. There's two ways to do this. One is by doing binary rewriting, as we do and as Microsoft does, and then you just kind of know, right? In fact, what we do is we kind of, if you count, well, it turns out all you need to do is count the number of backwards taken branches combined with the current program counter gives you a unique notion of time in your program's execution. So in the early days, we counted all branches, but just as an optimization, we now only count the backwards taken branches. There's another way to count branches, though, which is to ask the hardware to do it for you. And this is what RR does. So modern CPUs mostly have these performance counters. And historically, they weren't good enough Intel makes no guarantees about the precision of these things. Like, you should use them. It's for performance measuring, though, right? So it might be off by a bit, but it should be about there. Which actually turns out, at least for retired branches, they are currently accurate enough. There's a little bit of fudge factor needed, and I won't get into that. But yeah, so you can ask the hardware, how many branches have I taken, and then hardware to give it. So the advantage of that is there's a lot less code to write. You don't have to do binary retranslation, and it's nice and fast as well, right? It's a little bit of slowdown when you ask the processor to do that, but not much. But the disadvantage is the processor won't always cooperate. So in the demo, when I showed RR, I had to set my kernel event paranoid thing to 1, because by default the kernel won't tell you, because like all these Spectre meltdown style side channel attacks, there's sort of concerns that they could be used. As far as I know, there is no proof that they have been used in that way. And in theory, they kind of can't, because if they are deterministic, like they're accurate. So in theory, there isn't any information you can glean, but there's no guarantees made, so everyone turns these off, and they're especially not available in like multi-tenant cloud instances, because people are very sort of paranoid about that. But where they are available, where the CPU, and not all CPUs do it, so some AMD and some ARM do and don't. But where the CPU will do it, and where the operating system lets you have it, that's quite a neat way to know where you are in time. The other thing that binary rewriting lets you do, though, is to deal with shared memory. So one of the limitations of RR is that if you have shared memory, it can't cope. It has no way to trap, but we're doing binary instrumentation, so we can. Also, we talked about the non-deterministic instructions, get random number and things. Again, that if you're doing binary instrumentation, you can, like, it turns out when you're binary rewriting, you can kind of do anything. There's nothing, I'm going to regret saying this, but like, there's nothing that Intel or Linux or anybody can throw at us that you can't just figure out by binary rewriting. You've just got that control. So what we do there is, I'll just get into that a little bit because I think it's kind of cool, is, so it's a bit like this design trade-off at the beginning. So we want to implement shared memory. So what we do is, when an access is made to shared memory, a read from shared memory, we actually squirrel away what was read. And so the next time there's a read from shared memory, we say, has that value changed since the last time we read from it or wrote to it? And if it has, then we store an event in our event log. Otherwise, we can just carry on as normal. Now, but you want it, just doing that check to see if it's changed is relatively slow. So we don't want to do that for all memory accesses. Like every time you're accessing a stack or something, if we do that check, it's going to go really slow. Although, I'll get to both. So we don't do it for all memory accesses. What we do is mark shared memory as being with prot none, so it's not so it faults when you first touch it, and that allows us to figure out which instructions, at least some of the time, access shared memory. And then we retranslate those to do the check. So the nice thing is most instructions go at full speed, but the ones that do access shared memory, they get a little check. We don't want to fault every time it accesses shared memory, because that would be way too slow. And what the Windows one does, because so Linux and Unix in general has a really nice, well-defined system call ABI. There's about, depending what you count, there's about 400 or so different system calls. A little bit painful. We need to know what every single one does, what changes, what bits of memory might get changed, etc. But it's not that. It's like it's a tractable problem, right? Windows kernel has thousands, and no one, not even Microsoft, knows what they all do, right? It's not just just loads of them, and it's not a stable ABI. So Win32 is the stable ABI, and they're allowed to change the kernel ABI, and as long as they've got the right version of Win32 running on top. So this record the system calls and re-execute approach doesn't quite work on Windows. It's not really practical. So what they do is they do what we do for shared memory for all memory accesses. Every single memory access, they have a look, has it changed? So it runs a bit more slowly, but it just kind of deals with that Windows weirdness. Yeah, parallel phase it, that's fine. Cool, so. I'm going to go back to the other bits I was talking about was use cases. I remembered. Right. So yeah, so you can totally use this in production. Asterisk. I sort of say this because when you show this, the first thing most people think is, yeah, holy shit, that changes everything. And then I'm going to deploy this in production because that's where my hardest bugs are. Like if I've got a test case to reproduce it, it might be hard, but I'll get there eventually. I've got this customer that says every twice a week or something they get this problem, and I never reproduced it in-house, and I just want to do it in production. It totally works. We do it all the time with our customers. Microsoft do it all the time with Office. Actually, here's a little anecdote. So I went to see. I do two anecdotes. I like anecdotes. So I went to see the people who at Microsoft who built this, and it's before it was released publicly. So they came out of Microsoft Research. There was a paper out of Microsoft Research. Actually, I think it might have been in 2006, which is the same time as the omniscient debugger. They called it Nirvana, and it was all about how they do this, and it did the binary instrumentation. It was a research project. And then nothing else, sort of no mention of it again. So I just assumed, some researchers did this thing, they got their paper published, and then they went on to the next thing. And and then talking to some Microsoft, and then they, and then I was talking to some Microsoft Research people, and I found the people who did this, and said, I guess you just kind of didn't feel, I'm interested, like why didn't you feel that was worthy of productizing? And they said, oh, we use it all the time. More than 50% of our Microsoft Office bug reports now come with one of these time travel traces. And our product teams basically tell the QA people and the customer support people, get me a trace, otherwise I ain't committing to fixing your issue. I was like, wow, okay. So if it's so useful for you at Microsoft, why haven't you released this to the world? And they said, this is why they're much smarter than I am. They said, oh, because we knew it was going to be a support nightmare if we released it into the world. And they were right. Anyway, but they have now released it and it is publicly available. And if you just get WinDebug, for some reason, I just think they just haven't. It's not in the regular Visual Studio, but if you get the WinDebug, which is the kind of more powerful Windows debugger, it's just there. So that's been the case for a few years now. What was my second anecdote? Oh yeah, and they also did at Microsoft. They did a project kind of like Replay.io, but they did it in the browser in the JavaScript engine. And I got talking to those guys. Both teams worked at Redmond campus, and neither of those teams knew the other one existed until I introduced them. It was just mind-blowing how big that company is. Right, anyway, so everyone said, yeah, just use it in production, it's awesome, but please don't start there, because that's often what happens. People say, right, that's where I have the most pain, that's where the most value is, so that's where I'm going to start. Not usually a good idea, because it is, you kind of need to get used to, like, it's really, really easy to get started. I showed you how easy RR is, and you can download R trial, or you can use the Microsoft stuff. It's super easy to get started. But production issues are hard, right, by very definition. And if you just try and start turning this thing on in production, you're likely to struggle and then quickly decide, no, it's a nice idea, but it doesn't really work. Because there is, slowdown, and you need more memory, and you need to kind of understand the kind of dynamics of it, where you're really pushing the envelope. So start at the other end, actually, but maybe start in your CI/CD pipeline, right, in your tests. This is what a lot of our customers do, is what we do. So when there's two ways you do this in tests. You don't want to record all of your tests all of the time, because it's going to be too heavyweight, right? There's slowdown. On a good day, this stuff will run at half speed, right? On a bad day, it might be 3, 4, maybe even worse, slow down, 3, 4x, 10x maybe, depending on the application and everything. So you don't want to run all your tests with all this recording, and it chews up loads of memory, because it's just going to slow down your CI/CD pipeline apart from anything else. You don't want that. Also, highs and bugs are a thing. As wonderful as this is, it doesn't change the laws of physics. And so you're testing something slightly different than what your customers are running. So don't turn it on all the time in test. But what you do is, there's two ways to really make this work. you do it, we do both internally. So everyone always has some set of tests that you need to pass in order to merge some code in, right? Some people call it barrier tests, pre-merge tests, whatever. And you run that suite normally, and if one of those fails, you have the system rerun that test with recording, actually rerun a bunch of times with recording for some period, few minutes or whatever, and then hopefully you get a recording of that failure out. And then as an engineer, when you get the result back from your pipeline, oh, sorry, some tests failed, you now have the recording associated, and you can like just debug it there and then, and it really saves a lot of time. The other way you do it is everybody has, in all honesty, and this is all off the record, Chatham House rules, who feels they have like a bit of a flaky test problem? Show of hands. So it's 4, 5, 6 hands are up. 7, 8. Okay, so we've got about 3 liars in the room, I think. Well, in fact, someone did this talk a while ago, and someone said, no, I only want to deploy this in production because that's where all the issues are, and I don't have a flaky test problem. I thought, I think you need more tests. If all your tests are passing and your customers are sad, that's not a good place. Anyway, so if you've got flaky tests, you mark which tests are flaky. You run those as a kind of separate suite with recording all the time, and just leave it going, right? Again and again and again, and then this thing just poops out recordings, and then those failures. Then you can fix those flaky failures. Flaky failures are just a nightmare. Yeah, the only people who don't have flaky tests aren't doing enough testing, I would say, or lying. And then the other use case, which is where I recommend you start, is just in that inner loop development, right? I wrote that code. Did it work first time? No, because it never does, right? Let's not just your natural place is to go and add a printf, right? Because it's your happy place. You've been programming for years. You've been doing printf debugging for years. That's how everybody debugs right from the beginning. And so it's just your reaction. Stop. Use the time travel, and that's the way to start. And then that will be easier. And then when you've kind of got used to that, get it into your CI/CD, and then when you're then that's all kind of working, then start deploying it into production when you kind of know what you're doing. Right. How are we for time? Kind of getting towards the end. So that's all my slides, I think. So, just briefly, yeah, the snapshots are quite cool. So the way that most of these technologies do it is, well, at least on Unix systems, relying on fork. So fork gives me an inbuilt snapshot capability from the kernel. So when I say we take a snapshot, actually what we do is fork the process and leave that forked process hanging around. And then when we replay, you run the forked process. So if you sufficiently, if you PS and look around, you can see the processes. Yeah, but that is, I think, all. So there's, if you didn't get the QR code at the beginning, there it is again. Get your hands on $7,900 of software for free. Any other questions or discussion points? Yes, there's a question down in the back here.
So you mentioned that you can that you record shared memory. I took it as that doesn't include, like, if I have 2 threads in the same process. Like
yeah, right.
They could access arbitrary things.
Yeah. So threads within the process, yeah, we're not calling that shared, because what we do have to do is, so this is shared between the process that's being recorded and the outside world, when I say shared. Yeah. So yeah, let's talk about threads a bit. We didn't talk about it because it's an important one. So the way that most of these tools work is that they force some kind of serialization on the thread's execution, and then observe when thread switches are happening, and then when replaying, enforcing that exact same behavior, which sounds bad and is a bit bad, but not nearly as bad as you might think. So you still get any system calls and any I/O still works in parallel, and almost all race conditions are still reproducible with this. because you allow the thread switches to happen exactly as would happen normally at any point. You can even do stuff to make race conditions more likely. So we have a thing we call thread fuzzing. RR has a thing called chaos mode, which is kind of a bit similar. And they will like deliberately perturb the thread scheduling to try and make these race conditions come out. And when you have, so race conditions are all just the worst, right? And they're right on the top right hand of my chart at the beginning of like, they are by definition non-deterministic and tend to be these sort of silent killers where the bad thing happens and then not until a long time later do you realize, oh, that reference count never got dropped or whatever it was. So time travel is brilliant for race conditions because it's just, it makes those super hard cases really easy. And yeah, adding things like thread fuzzing and chaos mode allows most race conditions to be captured inside a recording. And then when you've got it, it's like, you can just see what happened.
Then just one comment. I tried WinDBG like half a year ago. It just crashed for me, so I'm still sad on Windows.
Oh, no. Okay, that's sad to hear. That's the first time I've, yeah, were you doing anything particularly exotic? Oh.
I was trying innocent stuff and everything exploded around me. I have no idea.
Okay. I don't, do they have a kind of support channel where, or do they just say?
I don't know. You can try to use the, I guess, Windows feedback button that looks like nobody will ever look at it. So
Probably, yeah. It's not a huge team. Yeah, okay, all right. You had a bad experience. Yeah, that's sad to hear.
So my question will be about user cases. So
yeah.
What about security domain when you do some research on malicious binaries where there are probably many anti-debug techniques involved?
Yeah. Yeah, so it's very, that's definitely a use case. It's kind of, I don't list it because it's kind of a, maybe a bit niche and also different level. Anyway, but but security analysis, like, trying to look for malicious code and understand what's going on. You don't have the source code. You can't add printfs. Super useful. Yeah, also just debugging something where, you don't have any access to the source code, like, at all. So, and you just do it at the machine level. Now, it's not easy to debug without source code or without debug info, but you can, right? And so I sometimes like to say that this stuff makes the difficult easy and the impossible merely difficult. So yeah, security, and we do have a number of customers in that space. I know there are others looking at security. That kind of security analysis is definitely a use case.
How do you deal with sort of systems with like graphics hardware, games? The data sort of going one way, but what if you've got like you're running compute on a graphics card and there's a lot of data coming back? Yeah.
So that would be an instance of shared memory. So the memory that the GPU is writing to, we would consider that to be shared because that memory is changing under our feet, if you like. Yeah. Yeah, one more question. Yeah.
What was the amount of effort to develop that technology?
Loads. Yeah, I used to have hair, right? Like, I actually remember, this is kind of embarrassing, but I tell you, okay, we've got a bit of time, so I'll do two embarrassing anecdotes. So, sitting down with my co-founder, some of you might know Julian Smith. I think you might know Jules. And we were working out how to do this. And I remember sat in his front room, and we said, I don't think it doesn't seem that hard, actually. I think we could make this work pretty easily. I think we figured it all out. No, it was really hard. It took like orders of magnitude more effort than I expected to actually make something that worked. And then but then it turned out the really hard thing was making anyone care. So my second embarrassing anecdote is, so we made version 1. They say, by the way, if you're not embarrassed of your first release, then you released too late. we didn't release too late. The first release was really ropey, but did work, did provide some value. Anyway, and we released, and I warned our web hosting company that we were about to make a release, and there could be there's probably going to be a lot of load on the servers, and they might want to think about that. I don't know what I expected them to do. Anyway, they said, yeah, okay, thanks for the heads up. We'll see how it goes. And I thought I'd phone some journalists and tell them about this, and it's just going to change the world. Everyone's going to be mind blown. Same reaction that I had. Of course, nobody even slightly cared, and it took ages. To get anybody it's really, really hard to get people to change their habits and pick up new tooling. Even, this isn't the only. There's lots of other cases. This isn't the only one. So, so all of it, both technically and non-technically, was so much harder than I imagined it would be. I'm glad that I didn't know, because I never would have started. Good. All right. Well, thank you very much, everybody. That was a nice session.